In this video, we're going to discuss stoichiometry calculations. All the work we've done in this unit leads up to this particular idea. We're going to be combining the stuff we've learned with naming, along with balanced chemical reactions and mole conversions in order to be able to predict the amount of product that a chemical reaction should be able to produce mathematically. Let's do a quick run through of the learning objectives in this video. We will start with a little bit of review. We'll talk about the law of conservation of matter and balanced chemical reactions. You should understand both of these ideas right now and have had a pretty good deal of practice on balancing chemical reactions. If not, I encourage you to go back and look over that material so that you're comfortable. We'll then come up with a definition for what stoichiometry actually is and what it does for us. We'll talk about the key component to a stoichiometry calculation, which is the mol-to-mol ratio. We'll identify what that is and practice how to create them. There's a flowchart we can use in this mathematical process. The problems are all very similar, so we can create a set of rules for how to approach pretty much anyone. And then finally, more than anything, we're going to invest some time doing a little bit of practice. Before we move on, I want you to notice the diagram on the bottom right. Stoichiometry has a bad reputation for being a very scary part of a chemistry curriculum, and it's stuff like this that I think gives it that reputation. This diagram is not something that I would describe as very useful. It's very confusing, very hard to follow. There are much easier ways to kind of summarize what we're trying to accomplish here. I guess what I'm trying to say is don't feel like you're doomed right from the beginning here, despite what you might have heard from others. This is a type of calculation that is very approachable. It's hard to figure out, but once you understand it, it is not difficult to do. So as we just stated, let's start this process by going over some quick review of some ideas you should already be comfortable with. First of all, we'll talk about the law of conservation of matter. This law has come up multiple times now throughout the year in a bunch of different contexts, but no matter how it comes up, it always means the same exact thing. That matter is never created and matter is never destroyed. All the matter that our universe started with is going to be the same exact matter that our universe ended with. Now, in terms of what we're doing here in class, this comes into play in how many atoms we're keeping track of and masses we're keeping track of. So previously, when we balanced chemical reactions, we talked about conserving atoms, having the same number of each atom type on both sides of the reaction, but this also applies to masses as well. And this is something you might have already come across when dealing with things like percent composition and combustion analysis. But if we start with 100 grams of starting material, when we undergo a reaction, even though it might go in different places, we will end up with exactly 100 grams of product. And it's this little idea here that we can exploit in stoichiometry in order to predict the amount of product formed based on the amount of reactant used. Secondly, we also talked about balanced chemical reactions, and this again is a product of this idea of conservation. Because we have to have all those atoms conserved before and after, we have to make sure that every atom we start with is the same as we end with. What we cannot do is change coefficient, or subscripts I mean. What we can do, however, is change coefficients. Instead of reacting one sodium atom with one chlorine molecule to get sodium chloride, we would act a certain number of these with a certain number until the numbers of sodium and chlorine are the same on both sides of the reaction. And if we were to go through that balancing process in this case, we would find out that we would get two sodium atoms reacting with one chlorine molecule to create two sodium chloride molecules. So again, it's really just a way of showing on paper the fact that we have a balanced chemical reaction by keeping track of numbers of atoms. So let's dive right into the meat of the actual topic itself. The question at hand now is, what is stoichiometry? Well, we'll start real simple. It is a calculation. Now that's very vague, but I think it's important to note that you're going to be doing some math when you're doing stoichiometry calculations. Perhaps something a little bit better. Stoichiometry is a calculation that predicts the amount of product formed in a chemical reaction. So if I'm going to perform a reaction, I should be able to predict in advance how much of each product that I'm going to be able to produce, how much product formed. Now, as I show here, this is actually based on a couple of things, so you can't just predict without having some prior information. First of all, we need a balanced chemical reaction itself, and that's what we were just talking about on the previous slide. A balanced chemical reaction is going to act very much like a recipe does when you're cooking in the kitchen. The recipe tells you how much of each ingredient is necessary, and it tells you how much product or how much baked good you're going to get as a result of performing that experiment. So we need a balanced chemical reaction. The second piece of the puzzle is the amount of reactant used, and this is equivalent to the amount of ingredients that you're going to be using in your baking project here. For example, the experiment might tell you, or the recipe might tell you you need 2 cups of sugar to get the job done. What would happen if you used 4 cups of sugar or 8 cups of sugar? If you increased all of the other ingredients likewise, you would expect to get more product out as a result. So again, it's what the recipe is, the balanced reaction, and it's how much of the ingredients you use, how much starting material is used in order to determine how much product is formed. All of that is going to get folded into a calculation that looks similar to what we have here on the bottom of the page. And all I want you to notice at this stage in the game with this calculation is that it should look familiar. We've lined things up in this calculation so that units cancel out. But instead of units canceling out like we did earlier in the year at dimensional analysis, these are units that are probably a little less familiar. These are chemistry-specific units. So really what we're getting into now is dimensional analysis again, but dimensional analysis with new units. And all of that's going to come together to allow us to do a stoichiometry calculation. Just to take this analogy a little bit further, here I have a recipe for a very famous breakfast food in the South, although I'm not a huge fan of grits myself. This is a recipe for making grits. And over here on the left, we see the actual ingredients for getting the job done, as well as how many ingredients are necessary in each case. Again, these ingredients are very akin to our balanced chemical reaction. They tell us that we're going to use 1 cup of this stuff, 4 cups of water, half a teaspoon of salt, 2 tablespoons of butter, and as a result of that, we're going to create a certain quantity of grits that's going to be produced. So all of this combines to make a certain quantity of grits. Now, in a lot of recipes, it'll actually tell you that in the process. It'll say it makes 4 dozen cookies, makes this many cakes, etc., etc. This recipe, unfortunately, doesn't, but we can imagine in our heads that a certain quantity of grits we'll get out of this. Now, if I took the same exact reaction, the same exact recipe, and doubled everything, I would be using more starting materials. And out of more starting materials, we would certainly expect that doubling this is also going to double the amount of grits that we actually produce as well. So by using more starting material, as long as it's proportional, we would expect to get more product out as a result. This is akin, again, on the previous page to how much starting material is used determines how much product is made. Ultimately, it's the two of these combined. It's the recipe and the amount of starting material used, and both of those are going to contribute again to the amount of grits formed. We're going to get into this more mathematically, but this is a nice analogy, I think, to get an idea of what factors are going to affect the answers of our calculations. So let's start talking a little bit more about this prediction process, the ability to say how much product will be formed based on how much starting material and a balanced chemical reaction that we have available to us. So up here on the top of the screen, I have a balanced chemical reaction. We're going to take the chemical substance propane, this is methane right here. We're going to be reacting that with oxygen gas in a combustion reaction, something plus oxygen, and we will expect to get carbon dioxide and water formed as a product. And as you can see, I already have the balancing coefficients added in here. 1 CH4 reacts with 2 oxygen molecules to create 1 carbon dioxide and 2 water molecules. From these ratios, the amount of each reagent and the amount of each product in the balanced reaction, we can start making some predictions. For example, if I react 2 molecules of CH4, so I'm going to start with 2 of these guys, we would expect to need a certain amount of oxygen and create a certain amount of product formed. For example, if I start with 2 molecules of CH4, I would expect to get 2 molecules of carbon dioxide. That's because, based on the balanced chemical reaction, there is a 1-to-1 ratio of CH4 to carbon dioxide. So for every molecule of CO2 I react, I expect to get every molecule of CH4 I react, I expect to get 1 molecule of CO2 out. Likewise, we can look at how much water we'll produce. For every 2 molecules of CH4, I get 4 molecules of water. Well, that's because we have a 1-to-2 ratio of CH4 to H2O. For every 1 molecule of CH4 formed, I would expect to get 2 molecules of H2O out. And that's really what we're showing here with this balanced chemical reaction is the idea of ratios. It tells us how these two chemicals are linked together according to this reaction. Well, we can continue this process. Say, for example, I react 2 molecules of oxygen. We can predict what we're going to get. We would expect to get, for example, 1 molecule of CO2. Again, we're talking here a 2-to-1 ratio. 2 oxygens gives me 1 of these, and I would expect to get 2 molecules of CO2 because, again, we have a 1-to-1 ratio here. For every 2 of these, we get 2 waters, which again is really just a 1-to-1 ratio. So really what we're identifying here is the fact that we're dealing now in ratios from our balanced chemical reaction as opposed to just the individual coefficients. And that's how you want to think about them from now on. Now let's take a look at this again, but in a little bit of a different perspective. We don't want to talk about numbers of molecules. It is not a very practical value to deal with. And in fact, we've created a whole new unit that allows us to count molecules without having to deal with those tiny, tiny quantities. And if you recall, that new unit is the mole. And if you recall, 1 mole is equal to 6.022 times 10 to the 23rd things. And the reason we like this new unit is because it's easier to keep track of a mole of atoms than it is to keep track of one individual atom. And it's very easy to relate these moles back to very practical units such as mass. So this is a much more convenient unit to deal with. The good news for us is that there's nothing different now in terms of what we just talked about. Because it's a constant number, 6.022 times 10 to the 23rd, it does not affect the ratios that we identified on the previous page. Let me show you what I mean. If I react 2 moles of CH4, I would expect to get 2 moles of carbon dioxide and 4 moles of water. If you look back to the previous page, that's the same exact ratio we had from before. 1 mole of CH4 gets me 1 mole of CO2. It's still a 1-to-1 ratio, and that ratio has not been affected because we've multiplied both of these values by 6.022 times 10 to the 23rd. So we can say 2 moles is equivalent to 2 moles, and likewise we can say for every 1 mole of CH4, we end up getting 2 moles of H2O, and we get this formal answer here. We can do the same exact discussion with the oxygen and have the same exact results. For every 1 mole of, for every 2 moles of oxygen we start with, we're going to get 1 mole of CO2. That's because this is a 2-to-1 ratio of oxygen to CO2, and this again is going to be a 1-to-1 ratio. It's the same exact ratios, except now we can talk about them in our new units of moles, which again just makes the mathematics a little bit easier on later. If you don't believe me, by all means, in the later problems, convert everything into molecules first, do your ratios like we just talked about, and then convert back out, and you'll see that that mole to molecule conversion always cancels itself out. You're going to multiply by 6.022 times 10 to the 23rd once, and then you'll divide by it later on in the problem, and it always just eliminates itself. This makes the math simpler. So let's start bringing this all together now into what the actual mathematics are going to look like. And to talk about what the actual mathematics will look like, we're going to talk about something new known as the mol-to-mol ratio. And this is really the key component to every stoichiometry problem. And really, we've already talked about it on the previous slides. Let's get some definitions down first as to what a mol-to-mol ratio is, and then we'll talk about how to create them, and then ultimately how to use them. So, what a mol-to-mol ratio is a new conversion factor made from our balanced chemical reactions. And again, that's what we were just doing on that previous slide. We were coming up with ratios, and maybe that's the word we should put in here, is the idea that it is a ratio from that balanced chemical reaction. What it does for us is it links the amount of one chemical used to the amount of another chemical formed. We can use that ratio to calculate how much product is made based on how much product we started with. It is made from the coefficients of the balanced chemical reaction. So that's the purpose of those numbers. The reason we always go through all the trouble of balancing is to use those coefficients in this mol-to-mol ratio. It is the key step in a stoichiometry problem. There's nothing else you're going to be doing today that's stoichiometry aside from the mol-to-mol ratio. Everything else is just going to be regular old unit conversions. This is the key step. And finally, it's only true. This ratio that you're going to create, in fact, let's point this out. This ratio up here that we're going to create from our balanced chemical reaction is only true for this reaction that it is made from. In a different chemical reaction, the ratios are going to be different, and they would apply to that scenario. So that's only true in one particular scenario. The good news is that they're easy to make, so it's not like we're going to have to make a big complicated thing every time we try a problem. Let's talk about putting some mol-to-mol ratios together, and we're going to use the same balance reaction we were talking about earlier. So for example, we talked about the fact that there is a 1-to-1 ratio of CH4 to CO2 because we see that from the balancing. This coefficient here is really a 1, and this coefficient here is really a 1. We can make that into a ratio. We can say for every 1 mole of CH4 that we start with, we're going to expect to make 1 mole of CO2. And we can use this now to convert between how much CO4 we have and how much carbon dioxide is going to be formed. Or, conversely, we could say if I formed a certain amount of carbon dioxide, I can go back and back calculate how much CH4 was needed. Likewise, we can make another one of these. We can say for every 2 moles of oxygen, I would expect to get 1 mole of carbon dioxide, and this would be a different mol-to-mol ratio that will allow us to link together oxygen and carbon dioxide. Depending on the context of the problem itself and what the question is giving you and asking for, you're going to choose which two chemicals to link together, and you'll make a particular mol-to-mol ratio to get the job done. And just like before in dimensional analysis, it doesn't matter what way you write it. For example, 1 mole of CO2 is equivalent to 2 moles of oxygen gas. It's okay that this mol-to-mol ratio is the flipped version of this. We'll figure out the right way to write it when we set up the dimensional analysis itself. The goal again is just to identify two compounds you want to compare together and then turn them into a ratio. And there's probably a bunch more of these ratios we can write, but I think you probably get the idea of what it is we're getting into here. Any two can be combined together. I guess if I was going to show you one more, I would say you could also do this. We could say for every 1 mole of CH4 that we react, we will need to combine that with 2 moles of oxygen gas. It doesn't matter that they're on the same side of the reaction. It's still a valid ratio, and this would allow us to predict how much oxygen was needed to react with a certain quantity of CH4. Any of these are valid, and again, it's going to depend on the context of the question itself. I think it's time that we actually take a look at an actual question. And this is going to be the first and simplest form of a stoichiometry calculation. In this problem, we're asked how many moles of carbon dioxide will be formed by completely reacting 10 moles of CH4 with plenty of oxygen gas in the following reaction. Now, really quickly, before we dive into this, we've got this little tag here on the end. By completely reacting 10 moles of CH4, and we also talk about the fact that we have plenty of oxygen. We have a certain quantity of this. We have 10.0 moles of CH4, and that 10.0 moles of CH4 can only burn if there's enough oxygen to combine it with. You can imagine if we ran out of this oxygen early, we would stop the reaction and we would never consume the full 10 moles, which means we would not be able to make a prediction. This is not something you need to worry about a lot yet, although there will be problems later on down the road where I do not necessarily give you plenty of the other reagent, and you'll have to figure out which chemical runs out first to do your calculation. This is known as a limiting reactant problem. For now, it's just a matter of using the number that's given and knowing that we have plenty of oxygen to react with it. Well, we already have the balanced chemical reaction. In many problems, this is something you will have to do on your own. And it turns out that this problem talks about carbon dioxide and it talks about CH4. If we take these two chemicals, sometimes it helps to actually box them in to remind yourselves of what chemicals you're dealing with. We can build a mol-to-mol ratio from this. And we can see that for every 1 mole of CH4, we're going to react and get 1 mole of carbon dioxide. And this is going to allow us to convert between how much CH4 we have and how much carbon dioxide we're going to get, which is exactly what the question is asking us to do. Once you've identified your mol-to-mol ratio, let's actually start the problem. We have 10.0 moles of CH4. We always start our dimensional analysis by writing down the given number, and we're going to put in a multiplication sign and a line to do our actual calculation. We've got to line up units. We're going to have to put moles of CH4 on the bottom and moles of CO2 on the top. And it turns out for every one of these, we get one of these. When we line things up, moles of CH4 will cancel out with moles of CH4, and we'll have an answer in moles of carbon dioxide. Hopefully you have not picked up a calculator to do this, because that answer is 10.0 moles of CO2 is what we would expect to get. Again, not surprising here, it's a 1-to-1 ratio of CO2 to CH4. If we start with 10 moles of CH4, we would certainly expect to get 10 moles of carbon dioxide out. And this is it. This is like level 1 of a stoichiometry problem. We have done exactly what we said we were going to do. We've taken the amount of material we started with, we've taken a balanced chemical reaction, which resulted in a mol-to-mol ratio, and we were able to predict the amount of product this reaction would form. As problems get more challenging, what will happen is you'll have less convenient units, meaning you will not be given moles, you will not be asked for moles as an answer, and that's going to require more steps. The important thing to note is it's always going to circulate around a conversion factor such as this one, a mol-to-mol ratio from your balanced chemical reaction. We just might have to do conversions before to get into moles and conversions after to get out. Last thing, before we give a problem for you guys to try on your own, notice my units. It is extremely important that you're very specific with your units. For example, I get a lot of students who just write this down, 10 moles. The problem with that is we got moles of different things. We got moles of CH4 and we got moles of CO2. Lining up this conversion factor can be difficult, if you don't have the actual chemical name associated with it. So from now on, please always don't just write moles, but moles of what it actually is. And that allows you to line up the correct unit with the correct unit so that things cancel properly. In this problem, it wouldn't have made a difference. In others, it definitely will. Here's a second problem for you to try, very similar to the first. You're going to need to balance the reaction first, identify the two chemicals you're going to be converting between, create a mol-to-mol ratio, and then finally do the actual conversion to figure out how much product in this case will be formed. Take a minute, pause the video, see if you can actually get an answer for this, and then we'll go through that answer together. So here is the balanced chemical reaction. 1 mole of propane is going to react with 5 moles of oxygen gas to create 3 moles of carbon dioxide and 4 moles of H2O. In this particular question, it's asking us to calculate how much carbon dioxide will be formed by completely reacting 5.5 moles of the propane. Again, a strategy you can use in these problems is underlining the words and then underlining the appropriate chemicals in the actual reaction. We got propane and carbon dioxide as the substances we're interested in. From this, we can create a mol-to-mol ratio. It turns out from every 1 mole of C3H8, we're going to expect to get 3 moles of carbon dioxide. And that's going to be the ratio we use to convert between how much of this we have and how much of this we're going to get. So in the problem, we're told we have 5.5 moles of C3H8. Put in a multiplication sign and a line. On the bottom, we have to have moles of C3H8, and according to our mol-to-mol ratio, we can convert that into moles of carbon dioxide. And for every 1 mole of C3H8 we have, we're going to get 3 moles of carbon dioxide. We have lined things up so that units cancel appropriately, and it looks like it's 5.5 times 3, which is going to get us 16.5 moles of CO2 formed. So for every 5.5 moles of stuff we start with, we're going to expect to get 16.5 moles of carbon dioxide created. Again, we have now been able to predict how much of this product we can make based on this entire reaction and the amount of starting material that we started with, assuming, again, that we had plenty of that oxygen. And that's, again, what I imply here when I say completely reacting. Hopefully you're seeing these problems as not being too challenging, but unfortunately, as I said earlier, they do get a little bit harder when we start introducing new units. So to help you with future problems, what I found online is a picture. This is called a Stoichiometry Roadmap, and it's basically a step-by-step process for getting you to work your way through these problems. The steps we've done, or the problems we've done so far, have focused primarily on this central region. We were given moles of our known. We could then use the mol-to-mol ratio, which is really the only part of this process that is really stoichiometry, and we were asked to produce the moles of our unknown as the answer. So this is the problems we've done so far. Unfortunately, those starting numbers typically aren't given to you in number of moles. For example, I can tell you how many particles you're starting with, what the mass is you're starting with, or what the volume is you're starting with. To use the mole-to-mole ratio, we have to know how many moles of starting material we have, regardless of how we're given the information. That being said, the first step in a stoichiometry problem is typically converting one of these values into the units of moles. Then we can use our mole-to-mole ratio. And then again, typically, I don't want the answer in moles. I want the answer in something I can use more practically in lab. Third step in the process will be then converting your answer into a representative number of particles, a mass, or a volume. Again, using the mole conversions we've talked about earlier in this chapter. Before you go on, a couple things. On the bottom of the web page here, you should be able to find a digital version of this map you can print out and carry along with you. You'll find this is probably very valuable in the beginning steps of dimensional analysis, but you won't need this later on. Secondly, if you are not comfortable with mole conversions, that is something you also want to take time to look into. Go back to the previous videos, review the process, practice some problems. If you can't convert things into and out of the unit of moles, there's no way you're going to be able to get correct answers for stoichiometry, even if you've understood stuff so far in this video. So in the next couple of problems, we're going to put some of this information to use and see if we can do some more advanced stoichiometry calculations. Here's another example of a problem to try. How many moles of water will be formed by completely reacting 45.71 grams of propane? This is the same reaction we had from before, but instead of being told how many moles of propane we have, we are now told how many grams of propane we start with. And as a result of that, we have to do some extra work before we can use our mole-to-mole ratio. The process, however, is still the same. We are interested in how much water we're going to produce, so that's one chemical we want, and we're interested in how much propane we started with. As a result, we can underline those terms in the actual reaction, and in this case, it looks like we're going to have a 1:4 ratio. For every 1 mole of C3H8, we're going to create 4 moles of H2O. As a result of this, we're going to start the problem exactly the same way we've started from before. We're going to take that given number that we have, and we're going to do some conversions, and ultimately resulting in our mole-to-mole ratio. So our given number, 45.71 grams of C3H8. We'll put in a multiplication sign and a line. Now, in previous problems, we jump right into this. This is stoichiometry. This is the thing that connects the amount of propane to the amount of water, which is what we need to do. But units won't work this time. We have grams of propane, and this conversion factor has moles of propane. As a result, if you go back to the roadmap from the previous screen, it tells you if you're given a mass, the first step is converting the grams that you have into a certain quantity of moles. But if you think about it in terms of dimensional analysis, this is what you have to do. If you want our units to cancel properly, we need to get this into moles first, so that in the following step, moles of C3H8 can cancel and result in moles of H2O. Well, looking back at your notes from earlier, if you want to convert from grams to moles, we need to know the molar mass of C3H8. So that molar mass is going to be the mass of the carbon atoms, which is 12.0107 times 3, plus the mass of the hydrogen atoms, which is 1.00794 times 8. So you got to look all that stuff up on your periodic table. Doing those quick calculations, I get a number of a molar mass of something in the vicinity of 37.048 grams per mole. We can plug that in here. We're going to have grams on the bottom, so that grams cancel with grams, and we're going to have moles of C3H8 on the top. And it turns out for every 37.048 grams, I get 1 mole. Again, you'll notice I didn't just write moles up here, I wrote moles of what it is. That's going to help us line things up in our next step. So we converted from grams to moles. That was the hint we got from our flow chart. Now we know moles of C3H8. Remember, you are always trying to get back to this mole-to-mole ratio here. That's the thing that does stoichiometry for us, and we're ready to use it now because we'll be able to cancel out a unit. For every 1 mole of C3H8, we end up getting 4 moles of H2O. Moles of C3H8 cancel with moles of C3H8. Again, notice writing this down here is what allowed us to line up the correct units here. If you left this C3H8 out, This step gets a little more ambiguous. Now we've lined it up. As of now, we'll have an answers in moles of H2O, and that's exactly what the question is asking for us. How many moles of H2O? Once you've got units to work, it's time to plug things into your calculator and get yourself an answer. And really quickly, when I do all the work here, I get an answer somewhere in the vicinity of 4.935 moles of H2O. I rounded to 4 significant digits to match the starting number I was given, and this is what we're going to be looking for. And again, when you really boil it down, all we've done is predict how much water product would be made based on how much starting material we would begin with and the balanced chemical reaction, which was expressed in the mol-to-mol ratio. This problem is exactly the same as the ones we've done before, with the only exception that we had to do an extra mole conversion in the beginning. I've got one last problem for you. This one I'd like you to take a swing at on your own before we get started. It's the same reaction. We have the same number of grams of propane, but in this case, what I want to figure out is if I have that 45.71 grams of propane, I will create those 5 moles of carbon dioxide like we talked about in the previous reaction, but now I want to know how many liters of oxygen gas are needed to completely react with that 45.71 grams. This is a very practical skill. You can imagine in a lab you'd have to get a certain quantity of each reagent together. This is a calculation you would use to figure that out. Take a minute, pause the video, use your flow chart, use the roadmap for doing stoichiometry problems, and see if you can figure out how many liters of oxygen are necessary to react with our 45.71 grams. We'll go over the answer in a minute. So let's see if we can't go over an answer here. We're going to follow the same process. In this particular problem, we're dealing with oxygen gas and propane as our 2 chemicals. It's important to go back and underline them in the reaction and then create a mol-to-mol ratio. For every 1 mole of C3H8, we get 5 moles of O2 needed to completely react, and that's again what the balanced chemical reaction tells us. Now once we have that information, we're actually probably ready to start the problem. We have 45.71 grams of C3H8. We're going to use information from the previous problem. We want to use this mol-to-mol ratio, but we're not ready to yet. We got to get grams into moles first. Now unfortunately in the previous problem, I think I told you that the molecular weight was something in the vicinity of 39. I made a little mathematical error. It turns out it's somewhere in the closer to 44.095 grams of C3H8 for every 1 mole of C3H8. That gets us into moles, and again the reason we want to get into moles is so we can use our mol-to-mol ratio. It turns out for every 1 mole of C3H8 we get 5 moles of oxygen gas. Grams here will cancel out with grams here. Moles of C3H8 will cancel out with moles of C3H8. And this is where we stopped in the previous problem, but this problem is a little bit different because this problem asks for liters of oxygen gas, not moles. We got to do one more step. Again, from your conversions now, we know that 1 mole of any gas has a volume of 22.4 liters. So this will convert us from moles of oxygen into liters of oxygen gas, and this ends up giving us a third step. And this is, by the way, what I would describe as a full-blown stoichiometry problem. They typically end up being 3 steps long. First step is converting into moles, second step is the mol-to-mol ratio, and then the last step is converting out. And actually it might not be a bad idea to write that down. In our first step, we're going to convert 2 moles. Our middle step here is always going to be mol-to-mol ratio, and our last step is typically to convert out of moles. This step always happens. These 2 steps only happen sometimes, and that sometimes is when the answer or the question either gives you information not in moles or asks for an answer that is not in moles. But you always have to do a mol-to-mol ratio or else you're not doing stoichiometry. Quickly putting all this into our calculator, we get an answer that's somewhere in the vicinity of 116.1 liters of oxygen gas at standard temperature and pressure. And that's pretty much what we're looking for. Again, what I want you to note with all of this is that it's really a very simple, repeated process. Wrapping your head around it is difficult, but once you've done enough of these problems, you're going to see it's the same thing over and over again. balance a reaction, create a mol-to-mol ratio, and set up your conversion here. That could be anywhere from 1 to 3 steps long depending on the type of information that you're given in these problems. But as I said, the name of the game here is practice. We'll be practicing this more in class, and you will definitely be practicing it on your own and in the lab as well.